Hi everyone, and welcome to our video on a tension or force problem with our vectors. So if we're trying to find the tension or force in each rope, what we really need to do is redraw it and then convert our vectors into component form. So what this 120-pound weight is doing is from the center, it's trying to go straight down like that. And what we really need afterwards is to also put our vectors with these little ropes. Okay, so if the weight's trying to go straight down, then these ropes are trying to pull it back up. So that way it stays in its normal position. So if these ropes weren't here, the weight would just fall to the ground. Okay, so we have these vectors also going upward-ish, upward and right, upward and left. Okay, so I'm going to call this W for the weight. And then I'll put my little vector symbol, and then I'm going to do F1 for force 1 and F2 for force 2. So, or you can call them T for tension. I'm going to prefer force. And after that, what now I really want is an XY axis so that I can start to measure these in the standard form. Okay, so we'll use the origin. So the W, let's color code. Let's do the W in blue. So W is going straight down. And our F1, I'm going to do in purple. Okay, so our F1 is something like this. But what I need out of it is this angle. Let's call it theta 1 for F1 and theta 1. And then my F2, let's get that sketched as well. Let's do that one in green. Is something like that. It looks sort of like in the picture. So here's our F2. And what I really need out of it is this angle, though. I need theta 2. All right, so let's get those. Well, it's using our, back to this sketch, how about I draw the axis into this as well? There we go. And then that way I can use the properties of right triangles. So if I have 32 degrees there and a right triangle here, I know that I can add this up pretty quick and say, well, that would be 58 degrees. And again, I have a right angle in that first quadrant. So then I would know that this one is 32 degrees. Okay, or you can even use alternating interior angles here is what also is looking like we've got. Okay, so this is 32 degrees. And then let's get theta 2 involved. Okay, so similar breakdown. If I had 55 and a right angle, and then we know that this angle here is 25 degrees. All right, so that adds up to 180 all the way in that triangle. And then in my green, well, I have 90 plus another 25, so that would be 115 degrees. There we go. Okay, so there's the two angles that I wanted, and even the blue angle, we can see that one real quick. That, we'll call it theta W for weight, is, well, 90, 90, and 90 is 270 degrees. Okay, so I've got all the angles. All right, and all that work there is to make it to where we can rewrite each of these. So let's write our force 1, so F1 in component form. So in component form, so I don't know the actual, so we're writing things in component form. Remember our vector, or you can write it in terms of I and J. I think I prefer component form though, is usually written as the vector, the magnitude of the vector, cosine of theta, the magnitude of the vector, sine theta. So that's how we often can convert it. Well, we don't know what those magnitudes are. That's what we're trying to find. So it says find the tension, the force in each rope. That's what we're trying to find. So we're trying to find the magnitudes of these. And I'm using the Solo absolute value. Remember that our magnitude, let's even put that here. Magnitude of vector V is written in different ways. Either the solo like absolute value or the double. Okay, so I'm choosing to do the solo to save a little space in writing. Remember, they are equivalent. So anyway, so all I'm going to do is say, well, we don't know what the force 1's magnitude is. That's what we're trying to find. But at least I can put in the angle. So they're saying it should be 32 degrees. And then still I don't know force 1 magnitude, but I know the angle. theta. Oops, I wrote theta. So we should change that to be 32 degrees. There we are. Okay, so there's rewriting F1. And then now we're going to rewrite F2 in component form. So still, I don't know the magnitude, but I'd have the angle, cosine of 115 degrees, and then still magnitude of force 2, sine of 115 degrees. And then we can get our weight. So, and here I'm still going to write it out the same way. I have the magnitude. Here I do have the magnitude. The 120, let's point that out. That is the magnitude of the weight, 120 pounds. So it would be 120 cosine of 270 degrees, comma, 120 sine of 270 degrees. Well, this simplifies. Cosine of 270 is 0. Sine of 270 is -1. So let's do that real quick and say it should be 0 and -120, which hopefully this vector makes sense because the weight's trying to go straight down. So there's no horizontal component. Remember, this is a horizontal, the first is a horizontal, and the second is vertical. The negative is trying to show the direction it going down. All right, anyway, so we've got our vectors all the way written. And then now we're using Newton's law. So if something is static, so if it's not moving, that means all of the horizontal components should add up to be 0, and all of the vertical components should add up to be 0. Okay, so let's now get that set up. So horizontal components sum should be 0. And then the vertical component sum should be 0. And vertical components sum should also equal 0. Okay, so for our horizontal, let's label it right here, horizontal, those are all of the first terms in our vectors in component form. So that means the magnitude of force 1, cosine of 32, plus the magnitude of force 2, cosine of 115 degrees, plus 0 should equal 0. Okay, let me mark this in blue. So the horizontal was taking our horizontal components, that one we simplified, adding them all up, and they should equal 0. And then our vertical components, let's do that in purple. So vertical, 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 those should add up to be 0. Okay, let me change it back to black ink though. Oops. Okay, so our vertical components, we've got the magnitude of force 1, sine of 32 degrees, plus the magnitude of force 2, sine of 115 degrees, plus a -120 should equal 0. Okay, and so what we're going to do with these two equations, let's label them 1 and 2, is let's rewrite them. So equation number 1, I don't need to show the plus 0. So all I'm doing is just simplifying a little bit. So we have the magnitude of force 1 cosine of 32 plus the magnitude of force 2 cosine of 115 degrees is 0. And our second equation, magnitude of force 1 sine of 32 degrees plus the magnitude of force 2 sine of 115 degrees. So the -120 we could add over and say it should equal +120 over there. Okay, so there's our setup. And these are variables. So F1 and F2's magnitudes are really just like X's and Y's. So what we currently have in this scenario is we have a system of linear equations. And what I'm going to do in this is let's solve for one of them. I'm going to solve for F1 in equation 1. So I'm going to solve for F1 in this equation, which means I just need to subtract. So we have F1 cosine of 32 degrees, subtract the magnitude of f2 cosine 115. So this is equal to negative magnitude of f2 cosine of 115 degrees. And then divide each side by cosine of 32 degrees to give us the magnitude of f1 is the negative magnitude of f2 cosine of 100, whoops, the degree symbol, 115 degrees over, let's see how much space I got, looking good, okay, over cosine of 32 degrees. Okay, so I'm gonna cloud this because that's now important to us. And then now that we've got it, let's sub it in to the other equation that we didn't mess with yet. Let's sub it into equation 2. Okay, so our equation 2, we're subbing in, let me mark it in blue, we're subbing in this here as all of this, that big fraction. Okay, and so what we've got, let's keep it in blue. Okay, so we're saying it's the negative magnitude of force 2 cosine of 115 degrees over cosine of 32 degrees times sine of 32 degrees. Okay, so now I'm moving on, sine of 32 in my equation 2, plus still magnitude of f2 sine of 115 degrees should equal 120. Okay, so the system of linear equations, we use the substitution so that we can change it into a single variable now. So now we should be able to solve for f2. And notice this problem does require a calculator eventually, but I want to save that for the final step. So I've been keeping my trig functions without plugging them in because I don't want these kind of random decimals throughout. I just want to save it for my final answer. All right, well, anyway, in this second step, so now we're trying to solve for the magnitude of f2. Notice that I do have, let's simplify it a little bit. So these are the same angle, sine of 32 degrees and cosine of 32 degrees. That means I could change that to tangent. It's not really necessary, but it might make things a little nicer. So one trig function instead of two. Okay, so I now have negative magnitude of f2, cosine of 115 degrees, tangent of 32 degrees, plus magnitude of f2, sine of 115 degrees should all add up to be 120. Well, these aren't very nice terms, but there is a common factor. So notice that f2 is in common. So let's factor that out. Okay, so I'm going to factor so that we have the magnitude of f2, because that's what we're trying to solve for. So I want to factor it out entirely. And I'd be left with negative cosine of 115 degrees, tangent of 32 degrees, plus sine of 115 degrees equal to 120. All right, so now to get f2 completely by itself, so this is the magnitude, so again, it's a variable, times whatever this number is. So this trig expression is just some random number, but I don't want it on this left side, I want it on the right side. It would be division. So we would divide that over. So the magnitude of f2 is 120 divided by negative cosine of 115 times tangent of 32 plus sine of 115 degrees. Okay, so this would be if we couldn't use a calculator. Well, I've got the calculator on my other screen. I am going to enter that in. Now, make sure, depending on your calculator, you might want to use parentheses in that denominator, just how I just wrote it. And so that way we can see what this becomes. Because chances are we're going to need to factor eventually in a second. Anyway, all right, so I've got it over on a calculator. Give me 1 second. I'm just typing it in. I don't think you need to see me type it in. That's why I'm not too concerned. Okay. Okay, so I've got, oh, I mistyped something. Okay, sine. There we go. Okay, so I got 102.5 to 1 decimal. So 102, let's do 2 decimals. So this is 102.53. And the unit involved with the force would be based on the unit of the weight. Okay, so pounds. So we've got pounds. Okay, so that was our force 2, as accurate as possible. So with no rounding until the very final step. So 102.53 pounds is force 2. Well, we also did need force 1. Well, that's why I clouded that equation. Force 1 is ready to go. I can enter the previous answer into that. Okay, so our force 1 would be negative our force 2. Okay, so that's the 102.53 cosine of 115 degrees over cosine of 32 degrees. Okay, so if I type that in, give me one more second. Okay, so we've got cosine of those. Okay, and we get 51.10 for our force 1. Okay, there we go. Okay, so these problems take a while, so we're almost at 20 minutes. Notice again, I tried to save the calculator for the final step. There's a lot going on, but I would say the main thing is trying to set up just your vectors in component form and working from there. Now, systems of equations might be a little rusty, but that's how often these problems go. So it doesn't matter how many forces they put on it, it's often done the same way. Now, if they did say, hey, what is your components of your forces? Well, again, I have those answers. So let me put that in green to the side. So we answered what they wanted, but if they said, what are your component forms, in case they do want that instead, then I am just subbing in the forces that we found back into our equations up here. So our force 1 was 51.1. So we would times it. Again, let me go to my calculator. 51.1 times cosine of 32 is 43.34, comma, and then same deal, but with sine would give us 27.08. And then let's do it with our F2 real quick as well. So our force 2 we found as 102.53. So 102.53 times cosine of 115, which gives us negative 43.33. And then one last one here. If we type that into the calculator, we get 92.92. Okay, and notice there's a little bit of rounding. Actually, that 51.1, oh no, so there's a little bit of rounding error. Notice that these two in the green, the horizontal in the green, notice these two do add up to be 0 with a minor rounding error. Okay, so that's again why we usually don't want to try to plug anything until the final step. Okay, and then notice these two add up to be the opposite of negative 120 because it's going in the opposite direction. So that's also a good sign, or they all add up to be 0. Okay, let me actually put that in pink. So these add up to be 0 as well. So the greens add up, or the yellow highlighted greens add up to be 0. The pink add up to be 0. That is, each of these things that we stated should be true based on Newton's laws. Okay, so everything's looking good. One last thing to mention about this is notice that our actual magnitudes of the force, 102 and 51, do add up to be 120, bigger than 120. That's fine, because again, horizontally and vertically, they do add up to be 0. Okay, so this downward weight, it's saying this second rope, F2, is doing most of the lifting, 102.53, to keep that weight suspended, whereas this other one is mostly is more horizontal than vertical. So that's why it's not taking much of a vertical load. It's got a lot less tension in it. Okay, anyway, that's it. All right, so long problem. If you do have any questions, though, please let me know. And I would say it's very important to try to organize these. Okay, so vectors. So this is engineering. This is the class called statics that you might be taking. It's one of the early things that is in engineering. Okay, so you can say, get used to these problems. Okay, so I hope you liked it. So it's nice and challenging. Okay, that's it. Thanks for watching. See you then. See you next time.